is there any specific thing that we need to consider during sample collection? Like, can we take it from the very top, or we need to take it from middle or bottom?
Yeah, that is very important. I did not put any slide on that. For the sample collection, if you take more, like say, fines, then of course you will get more binder. Uh, 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 and so you need to make sure that you have some fines and some course, like good representation of the mix when you collect the mix samples. Like when you do GMM, you have like kind of, you can, it's similar. If you take a plant mix, like you collect it by box for sure, and then now you need a little bit of it, right? So you just have to make sure you have, because if you have too much fines, what will happen is that the amount of solution that you use will be a little high, less compared to the binder you will extract. So the amount that we are suggesting, we tested that, okay, that's nice, and that can dissolve the binder. So there's the issue. And also, if you put more solution, it may not dry properly, with the time that you have. It's a field method. So I'm just saying that when you collect your mix, it has to have both fines and pores.
Okay.
Yeah.
Thank you for answering, and then the great presentation and the first session. And so I think it's 1:02. So let's get started with our presentation.
Thank you.
So let me just give a very brief introduction, or just of our presenter today. So we have Dr. Wasiuddin from Louisiana Tech University. So he's giving us a workshop on handheld FTIR spectrometer as a quality control tool for determination of SBS content in asphalt binder and wrap content in plant mixes. So in our morning session, we discussed about the polymer, how we can determine polymer using FTIR. This session will focus more on the wrap content determination, aging of binder, and probably we'll try to touch on the rejuvenator percentage as well. A few logistic. So this webinar series is brought to you by Southern Plain Transportation Center. And also Accelerated Bridge Construction, ABCUTC, which is led by FIU, Florida International University. They are also co-hosting this. And obviously, as always, Oklahoma Department of Transportation is helping us to organize these workshops. And if you have any question, please post your question in the chat box, or raise your hand. I will try to communicate those questions to our presenter. And also we are going to give 2 professional credit hours, 2 PDH, for attending the whole sessions. With that, the floor is your Dr. Wasi.
Thank you. Well, I'll just go ahead and start the second session. A little bit of background for those who are new in asphalt, maybe some graduate students. Use of wrap in hot mix asphalt. It is the most recycled materials, and also almost 99% wrap that we get is recycled. There are economic savings. You get aggregate, and some of the states like Louisiana, we don't have any natural aggregates. And also, like there is slightly binder is there, slight percentage of binder is there. So economic savings, and also environmental benefit. Otherwise, it will be just a waste, solid waste lying there. Use of 30% is allowed in some states, up to 40% we saw, and there may be more special cases, and in some states I do not know, but we saw it can be more than 30%, up to 40%. Average wrap use though 10 to 20%. It's very commonly mixed in work like in many states. 10 to 20% is common without any big changes in the mix design. Challenges. Wrap is always a challenge. We understand that's a highly aged material, so it can induce cracking. It has variability, like there may be the wrap may be coming from different sources, and it's getting maybe it's piled, and also the pile management may not be that good. In I saw, like now maybe most of the plants use shade cover for fines and also wrap. So that if it's not there, of course, it introduces variability in wrap. So use app wrap is, performance app wrap always in, kind of made actually because of this variability and proper management. Lack of proper characterization of wrap. We don't have, especially in the mixed design, we don't do much characterization that what classes of wrap 1, 2, 3 we are using. So it's not there much. Unknown degree of blending. So when we add wrap, how much wrap binder is getting blended with the virgin binder? We don't know that. So that adds lots of variability and uncertainty in our performance. Increased quality control effort is needed whenever you use wrap. So that's another additional thing to do, management, that quality control needs to be higher. So that's where FTIR comes in, that how can we use FTIR in quality control and assurance of wrap mixes. Now, now as we do use FTIR, here are the fundamental principles. As you can see that we have, this is our spectra, and within that limits of spectra, 650 to 4,000, you can see that there are some peaks that are unaffected by aging. And that's where it is used to normalize that binder concentration. So that's what we'll use this time. One of them is 1375, so 1600, 1455, 1375, and 2920. So these are the unaffected peaks of asphalt binder. Aging does not change these peaks. Now, the affected region, and very commonly used for asphalt aging in FTIR, is 1030, which is the sulfoxide peak, and it is here sulfoxide peak, and also the 1695, which is the carbonyl peak in this area. So this is the peak for carbonyl. So this is all we'll use actually for our wrap content determination. So now the need for the research is that, of course, we all know that, but still, that FTIR has been used for kind of as a supporting tool, not that, okay, we'll implement that and go there and measure wrap content. So because also those research were very much focused on binder aging. Very few studies were performed on mix aging, that how much binder in the mix got aged. Carbonyl and sulfoxide concentration increase with aging, as I showed you in my previous slide, that both carbonyl increases at 1030, at 1695, and sulfoxide at 1030. Now, which one is suitable for both binder and mix? So both binder and mix, which one we'll have to decide. And oxidation state and aging of wrap were not addressed. That how much, when you use wrap, how much does it get oxidized? So it was not addressed. And also oxidation state of different wrap, it was not addressed, that where does the oxidation of wrap with respect to PAV, RTFO, goes. So we actually try to understand that state of aging as we work with laboratory, different equipment of aging, field aging, and then again we add wrap and then we age again. So where do you stand actually overall with respect to different types of aging? So the goals actually we divided into separate ones, quantifying the laboratory aging of the binder and mix using a TRFTR, same tool that we used earlier. Selection of a suitable index. So for the binder and mix aging, so both binder and mix, that's purpose. Development of a quick extraction process that can be easily implemented in the plant and field. So we need a process, a standard practice. And I would like to say that Dr. Delmar Salaman was the consultant actually for all this project that we did. And he has many contributions on this project and other FDIR projects. So, and he actually is the pioneer to have a TR ASHTO spec that's provisional, that is to on the DR method, that means non-contact method. But this one is a little bit mildly destructive method. So we need some extraction because we used ATR FTIR. So, and then determine the wrap content in the plant mix. So we'll do that. Now, the experimental plan, I would like to discuss this because otherwise the data that I will show you to have confidence on the wrap content, you will not be clear. So, of course, we did laboratory, and I said that the focus of this project was also look at the plant and field samples. So, and then the laboratory aging, we did use unaged binder. We looked at that. So unaged binder, we used for 52, 58, 64, 67, and we can see that 50, 64 from 3 different sources and 67 for 2 different sources, 58 from 2 different sources. And then also all those binders we aged, we did RTFO and PAV aging. And then we did, when RTFO aging, we varied that. In my next slide, I will show you. And also when you did PAV aging, we varied that. And then also extracted binders. So extracted from the mix. So this is unaged. That means we prepared a mix, and then with different binders, we prepared laboratory mix. We extracted the binder, and we looked at the binder aging signal. And then we aged that mix. After preparing the mix, we aged the mix at 135 degrees Celsius. We aged that at different time durations, and also we aged that at different temperature, different time durations, and we looked at that. Plant factorial is very small, you can say. We looked at the 10 different RAB just to characterize or classify RAB, that what is the aging state of those RAB. And also we looked at the, for RAB content determination, we used 10 different plant mixes from 5 different plants. And then also, of course, in all those to determine the RAB content, you will know that we have to look at the virgin binder, we have to look at the RAB, and we have to look at the mix. So knowing this, we will, and knowing this, we can say that how much RAB it has, because beginning you had the target that you will add 15% RAB, but now how much you have added, we will determine it from the mix. So that's the purpose. So laboratory aging, when we use the RTFO aging, as we said, that we change the duration, and the purpose of all this is overall understanding of the mixing. And then also we used PAV at different durations, as I said, to understand, and we used multiple binders to analyze that, investigate that. Mix aging, like the lab aging, binder aging, we also aged mix 135, and these are the different hours that we aged the mix. And then also for the low temperature, we increase the time, like 1, 3, and 5 days. And for 135 high temperature, we used some hours. So now the quantitative analysis, we said that this is the area method. I think we discussed the area method earlier, so I'll just skip this one. And then now if we look at the aging, we can see that in case of aging, we say that we will look at 1695, which is the carbonyl wave number. So, and you can see that this is the from 1686 to 1720, we looked at, and we looked at the peak right here. So this is the peak height. And when we took the area, between these 2 points. So this is the area we took, and this is all we'll do is using this area at this range, at this 1686 to 1720. And this is our is a close shot that we can. So this is the one that unaffected area 2920. So we'll look at the area for 2920 along this range. And in case of height, we'll use the height right there. In the Excel file that we have for different peaks, as we just plug in the absorbance data for SBS content or maybe aging content, it will automatically calculate in different sheets, different peak will be calculated. So that's already set. We don't have to do any calculations there. So now I told this earlier that, okay, these are the two things, sulfoxide index at this point, so wave number, and then carbonyl index at this point number, whether we look at area or we look at height. And this is the unaffected by aging region. So we use two types of index. One is the height. So, and the other one is the area. Earlier you asked that question, why didn't I use or finally recommended area? So here we recommended finally the area. So this is the height. In case of height also, is not just the height, it is height at maybe sulfoxide wave number or carbonyl wave number, and divided by the unaffected, which is the binder concentration, to normalize that. So this is the unaffected height or unaffected area, where we divide it by to normalize that. Now, is just an example that how it happened. Say carbonyl index peak height at peak height for the carbonyl is 1695. We divided by the 1375. This is unaffected. 1456 unaffected. Just height at 1601 unaffected, and this is carbonyl height, and this is carbonyl concentration height. This is the unaffected peak height. So this is the peak height method that we did. And then if you look at the results for all those 5 different, one is without normalizing and others are with normalizing, divided by the unaffected one. So this is by this one by 1560. These are unaffected region that we divided, unaffected peak that we divided the carbonyl height. So, and then this is all, you can see that it does not, that it has its own relationship, even if we take green or blue or purple, anything we take, it has a significant increase as we PAV the binder. So this is just to show how different indices work. This one based on area, as again, I would like to address the last question. We wanted to see different indices always because we had the data. We didn't have to change our test anymore. So we checked lots of different and then if any simple index give good results, we just kept it. So this is in case of area that we checked with the unaffected region and the affected region. So now here, as I said, that I will give you the overall idea of any aging or how aging is happening here. We have like 8 different binders, 8 different binders, and then 4 different binder grade, 3 sources, and 10 samples of each binder. So here you can see that we have the from 3 sources, 4 different binder grades. and then lots of different binders. But if we look at its carbonyl peak, that no visible trend. Say this is 52, 58. So this is 58 is higher. But again, for 58, Mississippi is down. So we don't see that the grade has any effect. Also, we are seeing that the say 64, from different source, we could not find anything, any trend or anything. So we have also 67, Texas and Mississippi. So out of 8 different binders, so this is our carbonyl index based on the height ratio. So we did not no visible trend we saw. So carbonyl index, the conclusion was, so this is what we can take. Okay, let's look at the sulfoxide, sorry. And the sulfoxide index wise, also we did not see any trend. But of course, one question could come that why carbonyl is here even before any aging. So of course, there can be carboxylic acids, so and some other compounds that can produce actually some carbonyl index. So in neat binder, of course, you will see this carbonyl height or area, whichever you choose. So base binder without aging has carbonyl index. And then if we do sulfoxide index, we can see again that there is no trend. So we just say that base binders is no matter it's high grade or low grade, it doesn't have any trend. Now, what we do is that, as we said, that we did PAV aging at multiple cycles, and you can see that as we did PAV 1, 2, 3 PAV, this is unaged binder. As we did PAVs, our binder aging state carbonyl index is changing for 5 different binders, so it's increasing. And also, when we did the sulfoxide index, we can see that the sulfoxide index is increasing and it also decreases. So here we'd like to focus, we did focus here that why did it happen and is it true and how can we use any content wrap or anything and to if sulfoxide index reduces. So we really wanted to focus on that. So when we focused on that, here you can see that we have 5 different sources of binder and also a variable grade. So these are 5 different sources of binders and variable grades. And then we looked at the sulfoxide index, because in my previous slide, I said that the sulfoxide index reduces. So how to address that or how to work with that then? So if we look at this 52 binder, Louisiana binder, and then we can see that this is unaged binder index. And as we did PAV, then 2 PAV, 3 PAV, and 4 PAV. So it kept on increasing here. And then if we look at the PG58, it increases and it decreases. And you look at the PG64NC, it kept increasing until up to 4 PAV. And in case of 64 Mississippi, it reduces. In case of 67, it reduces. So it looks like that's what happens for some binders. Sulfoxide index keep increasing, and in some binders, it reduces. So here are some points in notes here. Sulfoxide index starts to decrease after certain duration of aging, of course, for certain binders. Sulfoxide can be decomposed to sulfones. So that may be the reason for the ones, say, for this binder and this binder to get reduced, resulting to reduce sulfoxide index. And sulfoxide index for RTFO, that comes from here. RTFO aged binder never equals the index of PAV aged binder. So this is another kind of fundamental properties wise, that as you can see that this is 1 PAV. So this is 1 PAV, right? The black one. And then if we look at the RTFO aging, as we kept RTFO aging the binder, the sulfoxide index increases, decreases, increases, decreases, all those things happening as we saw that sulfoxide decreases. But also there is something that it does not even reach Whereas binder stiffness wise, if you age just with RTFO a binder 24, binder aging wise is really very stiff. But here we can see that it does not even goes close to 1. So we kind of, that means sulfoxide index, it maybe it stops getting, it doesn't increase anymore. So that's why we thought that sulfoxide index cannot be a good indicator for RAP, where we'll have, or field aging, where we'll have extreme aging. Now, another thing we found for sulfoxide index, if we do for PAV and RTFO type of aging, just the binder aging, sulfoxide index, still you can use if you don't age it extremely high, like for PAV or that 8 hours, 10 hours of RTFO, then sulfoxide index still maybe for can be used for binder or laboratory aging binder. But look what happens if you look at the sulfoxide index for the mix extracted binder. This is the sulfoxide wave number, like 1030. Whereas at SiO2, SiO, which is the silicon oxide, their peak is right at 1000, right at 1000. So what happens is that there is shouldering of silicon into the sulfoxide area. So that's why when we extract the binder, it get influenced by the silicon oxide peaks, and then we will not get the sulfoxide index. So if you look at this chart, binder only, so this is the binder only, and then also binder plus DCM, which is dichloromethane. So we will use actually dichloromethane for extracting binder. So we wanted to check that whether dichloromethane has any effect. So binder only means you just, the way I told you in the morning, just you pick up some binder and touch it to the diamond, ATR diamond probe. But when you add DCM to it, so when you add DCM to it, of course, you are concerned if solution remains there, does that affect your spectra? So we saw that it does not affect. So, and also if we do, the next one is that if we make a mix without number 200 passing, and then we can see that still actually it does have some influence on the sulfoxide index because of the SiO. And then also filter to 25 microns. Say, our mix that you take is like you filter to the 20 micron, then you take your mix, you dissolve it to the DCM, and then you take out the like the dissolved solution where you have the binder and the DCM. Now you have to pour through if you pour it through a 25 micron filter. So that means your filter will take out all the very fine particles, finer than like kind of that passing number 200. So you can see that those also, it does not work as long as you use like any extracted from mix. Actually, you prepared a mix without number passing number 200, and you saw some area also and height. So what is the conclusion here is that sulfoxide index cannot be used for mix. So of course you will always have some particles into the binder that you extract and want to do the testing. So that will influence your spectra. Now here, so sulfoxide index, as you can see that it gets influenced by if you use mix, if you mix as any particle, sulfoxide index, actually it goes significantly increased. So what you do is that for mix, we decided from here that we will use carbonyl index. So not only that sulfoxide index decreases after certain aging, but also because of the silicon oxide peak, we will use discard sulfoxide index from here, and then we will start using carbonyl index. Now let's talk about the carbonyl index. So from now on, we'll talk about the carbonyl index. Now, as we aged the binder in the oven at 24 hours with RTFO aging, we can see that it kept increasing the index in carbonyl index. So it kept increasing, but of course at the initial it has a higher rate, and later on it has a lower rate if we look at the slope of it. And also, if we do the PAV aging, it almost similar. That is a little bit higher rate and a little lower rate. Same case of the PAV aging. Now, one thing we kind of looked at, just a note or observation, is that 24-hour RTFO aging, which is 0.0376, give us the value of aging at carbonyl index wise. Same amount of carbonyl index is there if we age the binder with RTFO 80 hours. So they are very close. So RTFO aging is very severe, but when it gets very aged, as you rotate the RTFO, it does not roll much and the thin film. So, and also it's not linear that we have found. So this is a comparison of RTFO and PAV aging. Now, if we look at the mix aging, that means you prepared a mix and then aged the mix at 135 degrees Celsius. So you mix aging, so and look at the carbonyl index. So it kept increasing like that. And also, you mix that you prepared, if you do that aging at in 4-step oven at 85 degrees Celsius, we see that keeps increasing. So here, one is 12-hour aging of 135 degrees Celsius, which is 0.0296. That's the index value. And then 120 hours aging at 85 degrees Celsius, and the value is 0.0254. So 12-hour is equal to 124 hours. So at higher aging, at higher temperature, it creates a really high rate of aging. You increase the temperature by 50 degrees, whereas it 10 times more aging here, if time-wise. So and then it's not linear. That's what also we are saying. Now, how to understand the state of aging in the wrap? So that also, as we mentioned in the test factorial. So we looked at that. So we went to the plant and collected wrap from 10 different sources, wrap piles. So and we went to 5 different plants, as we mentioned. So if we then we ordered the wrap carbonyl index, and of course there are 10 samples as we did, and you can see that this is wrap 1 and this is wrap 10. So of course it's put in order, actually order of aging, and we can see that it vary significantly. On the other hand, if we now want to compare, so this is the aging state of wrap, so it varies. And then if we want to compare that with the PAV aging, this is 1, this is 2, and this is 3, this is 4. This is laboratory PAV aging. And then now you can see that only, like the only 3 wrap has aging index lower than 4 PAV. That means the wrap that we see, there are 7 wraps here, they are much higher at aging state. They are at much higher aging state. They are higher than the 4 PAV. So that's what we observe when we compare different types of aging. So that's another thing, is that we wanted to look at what if we age the wrap. So we also took the wrap, and then wrap was aged at 135 degrees Celsius for 12 hours, just to see that how much wrap ages. So when we looked at, we found that wrap 1 we took and then we this is without aging, and then when we put that at 135 degrees Celsius for 12 hours, it increased. So RAP kept on oxidized, and carbonyl kept on increasing. And also the RAP that has highest amount of carbonyl index, so we kind of aged that at 135 for 12 hours, extracted the binder, and we looked at the aging index, so it also increases. So these things keep increasing the carbonyl index. We did not look at the rate. That's why, of course, it would be much higher than the increase in just fresh mix. Now here is one slide that also gives up some background of different types of aging, right? Here we have the PAV aging and the RAP aging. And as you can see in this figure, we have in the x-axis, we have the carbonyl index, and in the y-axis, we have the binder grade. That means the stiffness. Let's say this is the stiffness, which is the binder grade. Now, as we looked at, we have lots of RAPs. So as we check those RAP, as the carbonyl index of RAP increases, we did not see much increase in high temperature grade, because this is kind of very flat. As in carbonyl index increased in the RAP, but we did not see high temperature increase. That increase in high temperature grading or stiffness increase compared to what we saw in the PAV agent binder. In the laboratory PAV agent binder, when we increase as we increase the PAV aging, of course, we see that carbonyl index increases, but the binder high temperature grading does not increases significantly at higher rate than compared to RAP. So let's say I have a RAP and laboratory agent binder, and my carbonyl index in both those samples are same, which is a 0.04 carbonyl index. But the RAP one will show much lower grade than the laboratory aging, which will show this much. So that means in laboratory aging, you get carbonyl index increase, but what we see is that like laboratory aging makes it more stiffer with the similar amount of compared to similar amount of carbonyl index in a RAP. So the one that laboratory agent is much stiffer. So this is another observation that we had. Now the method that we used in this what we did actually before we went to the RAP content and everything, we used 4 PAV aged binder was mixed with unaged binder at different ratios. So we added a different ratio, this ratio, that 40% of aged binder, just to check that if we have a solid line or any hypothesis we make to determine the RAP content, is it valid? So what we did is that we added a laboratory agent binder, which is 4 PAV agent binder, which we considered as the RAP binder, right? So, and then we looked at that change in carbonyl index of the binder is linear with the concentration of agent binder. So as we added more and more RAP I just kind of say artificial or simulated RAP binder, as we increased more and more, our carbonyl index increases, and it follows a linear pattern. And then in this case, what we could do is that, okay, if we have any known ICO, which is carbonyl index, and then we can say, okay, this is the RAP content. So this is the hypothesis that you used actually to determine the RAP content. So we know the carbonyl index, and then we from the mix, and then we say that, okay, this is the percent of RAP, because what we did here is that we added different percentage of RAP binder, which is and then added that to the mix, fresh mix, and then we looked at the fresh mix index, said my fresh mix has carbonyl index of this much, and I made a horizontal line and a vertical line, and I consider, okay, my fresh mix has this much of aged binder. Now this is the better explanation here. Say I have a neat binder. So I measured the carbonyl index of the neat binder. I have a wrap, and then I use that wrap. So I extracted the binder from that wrap. So I have the carbonyl index of that wrap is this one. So this is for neat binder, and this is for the carbonyl binder, carbonyl index. Now let's say now what I did in the lab is that this is for aged binder, and this is for wrap content, which is wrap 8. We added like 16% of wrap. When we added 16% of red, we know that this is 0, this is 100. So 16% rep signal should be right there. 16% rep signal. So that means this is fresh binder. We took the signal. This is rep 8. We took the signal. We added 16% of red to the mix, and then we test the mix. So it should be right here if we test. But when we tested, we found for one sample, it is right here. Another sample we find right here. A little bit another sample we found right here. So we see that when we take the mix, so we took the mix, extracted the binder, do 10 samples, and then we found that this is the signal, which is 16%. So we tested in the lab with the real wrap, but we made the mix ourselves, and we saw that this hypothesis made with 4-PAV agent binder can be implemented for the wrap percent determination. We have to check the neat binder signal. We have to check the wrap binder signal, and we have to look at the mix wrap mix signals, and then just from this interpolation we can find what is the percent of wrap there. So that was the hypothesis that we continued with. Now here something a little bit different. I will get back a little bit because this question will come for sure, that what is a suitable index. So for suitable index, any index we choose, we looked at the root mean square error, which is the predicted value minus the measured value, and then number of data points, and then root over of it. So you just looked at, because there can be a minus there from the off, and then that can be on the other side. So you looked at the root mean squared method. So so that's what. Now this one slide we have to look at and find the suitable index, because we see that this prediction of wrap content work, but now going back to the index, what index we'll use. So I give you here some examples, though the top ones are height method, peak height method, and the bottom ones are the area method. So in area method. So in case of peak height, of course, we made the ratio between 1695 to 2920, and then 1695 to 1601, and in this 1695 to 1456. So this is the carbonyl height, and this is the carbonyl height. This is the unaffected peak height, unaffected peak height, unaffected peak height. And then bottom ones, as we saw that, see that this is the area method. So this is just the area at this one. This is area ratio, so which is this to this, and this is the area ratio, which is this to this. So we did that with many, as you can see, that you can make lots of indexes that we showed earlier a little bit earlier. So I'm just showing you some example, because the reason I'm showing it here, because because we chose finally this one. Well, you can, if you look at the RMSE, root mean square error, this is 34%, 13%, and 20%. Of course, this is calculated from the difference actually. So calculated from the difference. Calculated from the difference. So this is 14%, 9%, and 9%. So if I ask you which one has the least root mean square error, of course we'll choose that, and we can see there are two here. The reason we chose this one, that we'll look at the area ratio of 1695, which is carbonyl, and 1456. The reason we chose that is that we saw that this one better correlates right here at kind of the practical wrap content area. So now this one, if you look at, say, we want to measure 20% wrap, but in that area we see some inconsistencies or reflectance. So here we see that this initial data, it really fits well. This is your 0 and this is your 100. If you draw a line, it really fits well. 10%, 20%, even 40%, it really fits well. So that's why we chose this ratio to proceed on. So this is our final index for the wrap content determination. Now it is a really a field process. So what we did is the wrap collection from pile. So you can take out the top a little bit, as the ASTM sampling, like the kind of practice mentions. We just do is that we don't go at the bottom, we go a little higher, and then we take out 1 or 2 scoop out, and then we collect the sample. So wrap collection from pile. And then this is the mix collection. This is from the truck. So you can wrap, we have to take, and the mix we have to take. And then another thing we have to take is the fresh binder. So and the fresh binder, it's right at the tank. So we collect the tank. So we need, if you look at the previous this one slide, we need the this data, we need this data, and we need the mix data. And then so that we can predict how much asphalt, how much wrap is there. So here this part is very critical in the sense that that you can collect mix from the truck, and then you can collect mix from the conveyor belt to silo. So whenever it comes out from the mix, it comes out from the drum, you can collect the mix right from there. So there are 2 positions here that I want you to note right now. So here is an example that we collected, like the mix design information from here. So we did actually 10 different mix. I mentioned 12 here, but it's 5 different plants in North Louisiana. And also we went to actually close to Texas, in Texas. So wrap content, the samples that we did varied, and then nominal maximum size, it varied, sampling location. So this is the important point I want you to look at: outlet of mixing drum and the truck. So we collected sample from the truck and outlet of the mixing drum. So binder grade, the 10 different mixes we looked at, is 64 minus 22, 67 minus 22, 70 minus 22, and 76 minus 22. So we varied things a lot. Now, it's the HMA collection in the plant. So you take some samples. This is of course, looking at it, you can tell the fresh mix. So this is 100 grams of fresh mix. So I would like to pause here a little bit, and then I would like to switch cameras, and then give me 1 second. Get ready with your questions. So as we do this, so
yeah, I'm looking at the chat box. We have not received any question yet, but please feel free to post your question here, or just raise your hand to directly talk.
Yeah. So this is the, like the FTI, as I showed you earlier. So we need samples. So the way we collect, so we need 3 samples. One for binder. What binder you just touch it with the spatula. That here, and then that will give you. And I showed you that's very. So the other one is that how to collect the binder from the mix. We have 2. One is wrap we have to collect, and the other one is the mix. Now I have here a 100 grams, approximately 100 grams of wrap. So this is 100 grams of wrap. Samples are here. So this is our method that you can see it has both coarse and fines. So what I will do is that and then I will use something like this. So this is and I will put my 100 grams of mix into that. So this is, and then our method says this is kind of mild, quick extraction process that we say that we will follow. So this is what it is. I want to show you this one because fresh binder data you will get. Now you need two other data to do the wrap content determination. So of course that. Now you see that this is just a regular glass jar, but this is a beaker where, like you can see that this is written the so I will, how much you add, so I will add to this like this 100 ml of 100 ml of DCM, dichloromethane. So roughly 100 ml of dichloromethane you add. And this evaporates very quickly, I told you. And also I told you that it doesn't have any peak. It does not influence your peak at all, binder peak at all. So we don't have any issue with that. So now I will this 100 ml and 100 grams of wrap, 100 grams of, I will add actually 100 ml of the DCM into it. So dichloromethane, so that's added. And you can do that. So we say in the final that we will do that, keep that like this for 5 minutes. So so it will be like this. And then I see that already actually binder got separated. So this is, we'll keep that for 5 minutes. And then you can shake a little bit at the beginning, but also you want to like that kind of keep it last 1 minute. Maybe you can just keep it still so that all aggregates and fine particles it settles down because this is a weak extraction process. We can give more time to another 5 minutes to settle down now. So I'll keep it like this. So I will not go to the slides. Say so I'll move to the next step. So this is just doing it. I can see some large particles also already clear, and I can see that. So I'll wear the other gloves. So so uh, so as we do that, so like we after 5 minutes, what we'll do is that we'll use this PAV pans, and then we will pour it into the PAV pan, and then we'll wait till it gets like a DCM evaporates. Now the thing is that it takes uh, really 5 minutes or so in the field for DCM to evaporate. But in the lab condition, it takes a lot of time. So when we did, if we have, whenever we had samples from the field, like the fresh mix and also wrap and the knead binder, and we did the test in the lab, of course, when we extracted the binder from the wrap or the mix, we put that under the hood, this PAV pen, and then we kept that overnight, and next day we checked. But in the field condition, it really evaporates. So if you want to do that faster in the lab conditions, of course you have to use a fan so that it quickly evaporates. So that would be the faster way to do that one. Say so what next step on this one, but we did that. It's 5 minutes is fine for the field condition. Even if it does not fully DCM goes, as we checked it in many times, and we reported those, that the DCM signal does not influence your peaks. So that's it. Now, what we'll do is that this is 80 micron filter paper that we use. So this filter paper, and I will use a funnel. So I'll use the filter paper and the funnel, and then pour out the liquid through the filter paper. So I'll assume that 5 minutes is over. So I will just now pour the liquid into the paper, through the filter paper into the PAV pen. Oh, you can use another beaker actually. If you feel not comfortable, you can pour it into the beaker, as I did. You don't need you just need the binder. So you can pour it nicely. So all my materials are right here into the beaker. All my aggregates are right there. So I have poured it. All my liquid is there. So now I will wait, and then so that my DCM is gone and you have thick layer of asphalt. So next, what I will do is that I will scratch out, when the DCM is gone, I will scratch out the binder and put that into the FTIR probe. So that's the method. That's the mild extraction method. There is nothing special in it. It works. If you want to look at I will show you some pictures that how much aggregate is there, like there, how much washing is done. So we'll look at, and also we'll look at the data, that how much like accuracy we get with respect to the wrap content. So I'll show you all those, and then but we maintain this method that we followed in this case.
Yeah, Dr. Wasi,
Yes.
we have a raised hand from Jack Yusef.
Yes. Hey.
Hi, Wazzy. How you doing?
Good afternoon, Jack.
I
Thanks
was
for
wondering,
joining.
have you done a burn off of your aggregate after you've done the extraction?
Can you repeat, please?
Have you done a burn off of your extracted aggregate to see if there's any residual?
Oh, like how much is
asphalt?
the asphalt content left in the
Yes.
aggregate?
Yes.
No. When we published this material, we got review from ASA Journal of Materials in Civil Engineering. We published that paper, but the reviewer was really asking us that how much asphalt content you have left with, and how does the aggregate looks like. So what we did actually, we showed them in the rebuttal, we showed them some pictures of the like the binder extracted aggregates. So no, we did not do. The answer to your question is we did not burn the aggregate. No. I'll show you some pictures maybe
Okay.
now.
Thank you.
Yeah. Okay. Thank you.
I think Dr. Zaman is also raising his hand.
Yes, please. Yeah, sure. Good afternoon.
Sir, you are muted. Sir, yeah, we can hear now. Yeah.
Okay, can you hear me, Ashik, now?
Yes,
Yes,
sir. Yes.
yeah.
Okay. So I have two questions. So one, is it possible to actually find the critical aging of RAP using this method? And the second question is that could you also uh, you know check the repeatability? So in other words, let's say how accurate you have some bar uh, you know diagram in your graph, which is very good. So what is the repeatability if I have, because RAP can have a high degree of variability, right? So how repeatable is this method? Those two questions, critical aging and repeatability.
Yeah, thank you very much. The first one I can tell now. The second one, actually, that I have to show more slides. The first one is critical aging. Mm, if the critical aging, if it is defined by the carbonyl index, then we did not reach it, because how do you maybe the mix could have been aged more and more in the oven at 135, so we'll reach quickly maybe that critical state. And also, as we're seeing a plateau there, and so maybe we saw that the rate reduces. So we mentioned in subsequent slides, actually multiple slides, that it's not linear as we are going to higher or state of aging. It does not remain linear. And then, of course, and also it gets flatter. So maybe a plateau can be reached. And in case of sulfoxide, though, if we say critical aging with respect to sulfoxide, of course, we saw that sulfoxide index, it reduces. And then how to stay and check more, and also sulfoxide index in the field mix, it's not possible to check the sulfoxide index of the mix because it got influenced by other peaks. But in case of lab binder aging, there is limitations in RTFO. If we run too much RTFO, it does not roll anymore. So no, whatever we did, we can say that it could be a critical, but is it due to that we don't have the mechanism to age that more, or is it or our method cannot age more, or binder really gets aged to a critical state? Uh, maybe it is because of the way it ages in the road and the way it is ages in the lab. It cannot just age more, so there may be a state of aging that it reaches after that. So critical aging, I see that it can be maybe reached as maybe some researchers may be saying. So there could be but we really did not go up to that state. The 10 different reps, we saw that like 10 different levels of aging, and we exactly do not know how much carbonyl index we could reach uh, uh, before it does not age anymore. Maybe it's there. So, and the second question, I will show more. I want to show more slides. So, yeah.
Thank you, Dr. Rossi. Please
Thank
go
you.
ahead with your.
Okay, so give me 1 second. I need to change. Okay, so here we are with the extraction, and I know as like we had a question that how much of extraction do we really get from here? So this is what we're seeing. So this is the picture of the mix after extraction. So this is how much we did, and if our data is kind of more accurate, or we can get some accuracy with this type of extraction procedure, we can go on with that. So we just sorry. So this one, you get that, and then you keep this way, so it gets evaporated, and then you just extract it from here. So, and then exactly same thing as if I switch camera, you'll see, or maybe you can still see that it's getting dried. So, but there is not much flow of air at all in this lab. So, now here is the example for the like the variability. But first, I would like to show you something very critical that I asked you earlier. This is the testing where mix was collected from the drum. So mix collected from the drum and then mixing drum. And these are the cases where mix was collected from the field. So in our case, our study, so this is the binder binder signal carbonyl index. This is the RAP carbonyl index, and this is what it should be. Like, say, the amount of RAP it was used. If we interpolate, this is 0, this is 100. Let's say there is 15% RAP. So this one, this dotted histogram, this one is for the calculated, that it should be there. But our data points for the drum is very close. We did multiple samples, right? So all are right there. Now, if we collect it from the truck, as you can look at these three, highly short-term aged sample shows higher carbonyl index than the calculated index. So this is the calculated carbonyl index. This is the calculated for mix B, E, and H. And this is the data that we got. So our recommendation is very straightforward here, that collect your mix sample from the drum to know that how much is percent of RAB that you have used in the mix. So it should not be after the drum. So it should be from the drum and not from the silo or truck. So carbonyl index is significantly affected by the short-term aging of the mix during the production and storage. So that's our very straightforward conclusion right here. Now, what about the other mixes that we collected? So here is the result for the other mixes, and I'm almost at the end. So this is, I think, what everyone wanted to see. And I think the question also we had on this one. So this is the one that is the percent of mix that was added. But our sample shows that, which is 16%. So the red diamond is 16%. But the samples that we had, we collected samples, fresh mix samples, and then from the drum. So these are all the drum samples. We found 18, 14, 13, and the 10. So these are the 5 samples we collected from the drum, and then right after the drum. So these are the percent we got. For 16%, we said 10%, we said 18%, but the right percent that was added was 16%. In this case, we can see that 15% was added, but we got 11%, we got 20%. 16% was added, 15%, 70%. So in this case, our results are very accurate. In this one, which has the highest amount of RAP mixed in our study, where which is 26%, we got 36 highest and we got 25 lowest. 16% was added. So 15, 16% is very common here. And you can see that we got 10, 11, 16. In this case, 17% was added at 12 and 20. So determined RAP content varies within 8% of the designed RAP content. That's what we are seeing. So now what I would say here is that that it's not a trend that high RAP content, low RAP content is just everywhere, the data, but if we collect it from the drum, we can see that this is very close. Now, here is the point, that the variability of the RAP we had, it may not be that the method is incorrect. It may be that the blending means, like the binder when it gets added, the wrap binder, because our signal has to come from wrap binder and the fresh binder when we extract it from the mix. So the blending did not happen properly. So that is one big source of variability that we can have. But it is not the problem with the method you are doing. It is the problem with that the binder is not getting mixed with the wrap properly. So those error may come from there. Another one, the error may come from another source, is this one, that we are interpolating between these two. And when we are interpolating, but this binder, the fresh binder, we're taking it right outside from the binder tank. But what if whatever this fresh binder is getting itself aged when it comes to the mix? So there may be some aging of the fresh binder RTFO, but that did not influence our data or wrap percent too much. Maybe more study could be done that how much fresh binder get aged. In our case, maybe it did not happen. It did not influence much because of the high amount of aging that we go through with the wrap. So high amount of aging in the wrap. So it may happen because of that. So that is another source of error that could happen in this case. So that's one of them. Blending didn't happen. The other one, fresh binder, may have some aging when it is going to will have some aging in that. So we did not consider that one. But this is our field validation that we can up to how we can go up to. So, and then even if the wrap pile variability in wrap, so if you have wrap that is really high age at some portion of the pile, so that will show that you added high wrap content, but you did not add high wrap content because because of the variability in your wrap pile, it may just show that you have really high wrap content. Now the 30 minutes is enough to determine the wrap percentages in the field, and we are saying that the wrap extraction is about 15 minutes. And then while you do mix extraction, it's about 15 minutes. Simultaneously can grow as you collect. And then 3 replicas of FTIR binder. So you can do, and then that's not adding because fresh binder, you don't have to wait this 15 minutes. Fresh binder, you can just collect fresh binder signal. And then 100% wrap. So this, and then this from the wrap, you need to collect samples. So another 5 minutes, and then data analysis. And as I said, our Excel file, you just extract it and put it there. It will automatically calculate for one spreadsheet is for wrap, sorry, SBS, the others are for wrap. Different peaks, all will be shown there. So that's all actually. We have some conclusions. Carbonyl index can successfully quantify binder and mix aging. Sulfoxide is not adequate to conclusively determine the aging of asphalt. RAPS possess much higher carbonyl index than that of the laboratory aged binder of the mix. We showed one curve that RAP has more carbonyl. A quick extraction process can produce enough binder from the mix for testing of FTIR. That is what we really need to do in the field, a quick extraction process. So we went ahead with that. The amount of wrap can be determined by spectral analysis of the fresh mix. So, so that's the conclusion, and we showed you some field pictures. So I would like to answer any question you have on this one. So that was the last slide we have, and also it's 2:15. So
yeah. Thank you, Dr. Rossi, for very informative presentation and conducting this workshop. So we are open for a question. If you have any question, please feel free to unmute yourself or unmute yourself and shoot the question, or post it in the chat. We can still communicate that question to the presenter. Yeah, and Dr. Zaman has a question. So yeah, please, Dr.
So,
Zaman.
so one thing was I wanted to ask you. First of all, wonderful job. This is really helpful. And for the audience, I think we would like to do more. The SPTC would like to do more of this type of workshop. So if you'd like to see, other topics covered, so please make suggestions, offer suggestions. So one thing was it that I wanted to ask you that the duties are trying to increase the amount of RAP in mixes. So in your
Yes.
case, I think you have kind of some limited level. So do you have any plan to actually do or extend this study to include higher percentages of RAP that would be more
Sure.
reflective
Yes.
of what
Yeah, that
of
would
the
be,
duties are trying to
like
do?
yeah, so that will be great to do. I think within the background information of different aging we have, maybe it's I don't see that our RAP index or any index will like have any issues or limitations in that regard. It's just that plans they are not using. So we have to make maybe special request in that study that please use 40% RAP because they were not using the plans that we checked, we worked with. We could not find a plan making mixes with 40%. Uh, uh, um, so, uh, so we can, Louisiana does allow 40% for base mixes. So maybe we need to find good projects or where the producer will add 40% or even higher RAP in the mix. So that would be
Yeah.
great. That would be great. Yes. Yeah.
So Wasi, I think we have probably David in the audience. I'm not sure. So maybe I think David, if you want to share Oklahoma duty, how much RAP are we planning to include in the BMD and also maybe even in other mixes?
Dr. Zaman, I think David is not here in this in the afternoon session, but he was here in the morning session.
Okay, yeah, sorry.
I have a question here. So about binder and mix aging. So we have seen that the I know that the R30 actually allows for a 5-day for mix aging, especially it goes for 5 days at 85 degrees Celsius. And you are showing here that the on the binder aging side, if we go for uh, 12-hour 135 degrees Celsius, it shows almost similar or a little bit maybe higher aging than than the 5-day at 85. So do you think the mix aging protocol could be changed based on this?
Yes, this is carbonyl index, and we cannot go to sulfoxide index. We can see that aging wise, this is what, and that's the purpose of using FTIR really. That why not we look at the what is the chemical changes that are being going on. So and that's what we found. Now there may be one thing that if we take mix, if we age that in the lab, like does it really will say again about the RAP? But I think that your question is not along that line. Your question is comparing 85 and 135,
Yeah.
right? So
Yes, yes.
I think that's pretty much it. Because also because the other chart I wanted to that got confused maybe many that it is the difference when it is coming if you're using the grade of the binder how that change. Sorry, looking for that one. So it's not even that, but if it is simply like changing the chemical composition of it, that recommendation can come from also not only from binder grade change. I'm just saying that how much when you extract how much you get from how much modulus you get from 5 days, and then but also it depends on carbonyl changes and sulfoxide index changes. So I'm sure I think that it should be it should be checked also, that not only the modulus but also the carbonyl index. I do not know the full study. I have not read the full report of that study, but that recommendation and the study. But I strongly feel that because these are the chemical changes that are being inside the binder, and that's where the focus is right now. That our grading it needs to be more wider. It should also consist or take into account the effect of the chemical changes.
Thank you very much. One more question I have here is, was the 100-gram mix sample in the field split? Was the sample split to get the 100-gram, or it was just randomly picked?
Oh, this 100, yes, that's actually you asked the same question also, right? So when I picked up this 100-gram samples from the, I can give me 1 second. I'll show you that this is the box. So this is the ERAP box, right? You can see. So this type of box we use, and then it is collected from Diamond B Monroe. So we call it E, we named it, and then we wrote the details on this. So this type of box, when I picked up samples from there, no, it was not splitted. We randomly took, but only consideration is you have like good amount of fines and good amount of coarse particles in it. Maybe the variance, if you look at the chart right now, in the slide, there are variants, right? So maybe those things need to be looked at. But RAP, what gradation or how do you you can split it up, but exactly what is the gradation of RAP, we can check and take that composition. Yeah, so you can do that, of course, sieve analysis and then take that, but overall that can be included, that okay, this RAP pile has a this is the sieve analysis of this RAP pile, so we'll use that amount. But I don't think that the person who has that question just wants to know that how can you can take more representative samples. So that will increase. I did not, but that will increase the repeatability. Yeah, and that will increase the accuracy. Yeah, I agree.
Thank you, Dr. Wasi. I don't see any more question. If you have any more question, I'm just giving maybe like we can allow 1 or 2 question if you have any, or if not, I don't see anything, or please raise your hand or unmute and just shoot the question. Hearing none, I think thank you very much, Dr. Wasi. Thank you for this presentation. Is really great and informative, and I believe all the audience also enjoyed it. And please give a round of applause, virtual round of applause for Dr. Wasi.
Thank you very much.
Yeah, you did a really nice job. So for the audience, thank you to all of you for joining today and being with us, spend your time with us today. As Dr. Zaman already mentioned, we are going to organize more and more of this workshop, webinars, and short course. Please let us know your preferences, your choice. You can email us. You can reach to us through mail or other communications. So please let us know. We'll try to address those. We'll try to help the transportation community in Oklahoma as well as the Region 6. So thank you for being here today. We'll see you in our next webinar. Thank you.
Thank you very much. Bye.